study book with real analysis. Oh my gosh, same for spring break, and I think I have like more students than I usually do. Thanks to my 11th class in May. Plan for today, focused on open sets for the last class and a half. We're going to talk about closed sets today mainly. Yeah, office hours, it is crazy. So don't forget, you do have an exam on Wednesday after the break, in-class exam, and then I'll give a take-home exam that day as well. Homework 6.5 is up, but more importantly, some fun. Surprise! Homework 5 graded. Bet you didn't expect that 2 days after homework 4 got back.
Adam sure didn't.
Yeah, no, I lost that bet.
Adam now owes me ice creams because I made that happen. Yes.
Did you grade it so quickly just to beat Adam?
Pete, you don't have to rub it in.
Like, was that already the plan? Like, it's a little out of character, so.
Out of character?
Yeah.
I am Dr. Kevin Gerstle, we met. I think that's totally in character.
No,
because I wanted one less thing to have to grade over the break.
Yeah,
so over the break,
for like a week.
Say what?
Usually we have to wait for like a week.
Surprise, surprise.
Yeah.
So over the break I'm going to get caught up on all my grading, is at least the plan. So for you all, that means I'm only one homework behind at this point. Haha.
Nice.
And as well as kind of straggling homeworks that got turned in late that I kind of still have sitting in my desk in a pile. Yeah, any questions or comments before we get started for today?
What are you doing for spring break besides catching up on grading?
Eating that delicious ice cream that I've been on. Other than that, I don't know, relaxing a little bit. I got parents coming up for a couple days next week, so hang out with them some.
Why no?
So you go share the ice cream with them?
Adam, you gonna get my parents ice cream?
Hyperbolic that comes out in 3 days.
Yeah, indeed. All right. So one day, several people were asked, "What is 2 times 2?" The engineer whips out his graphing calculator, presses a bunch of buttons, and finally announces, 2 times 2 is 3.99, plus or minus 0.01. The physicist consults her technical references, sets up the problem on her computer, and eventually announces 2 times 2 is somewhere between 3.98 and 4.02. I am 98% confident. The mathematician thinks about it for a minute and says, I don't know what 2 times 2 is, but I have a proof that an answer exists. The philosopher smiles and asks, what do you mean by 2 times 2? The sociologist says, I don't know, but it sure was nice talking about it. The behavioral ecologist concludes 2 times 2 is a polygamous mating system. And finally, the med school student says 2 times 2 is 4. The others all look at her astonished. When she's asked how she knew it, she says, oh, that's easy. I memorized it. Alrighty, so last couple classes we focused on looking at definitions and properties of open sets. We said that a set is open if given any point in the set, you can find some epsilon neighborhood of that point contained entirely within the set, where an epsilon neighborhood of a point is just some open interval centered at that point of radius epsilon. And last class we proved that if you take any amount of open sets and take the union of all those open sets, meaning take all the points that are in at least one of those open sets, that union will still be an open set. And that's true no matter how many open sets you have. Finitely many, infinitely many, even uncountably infinitely many. And we also showed that if you take finitely many open sets, the intersection of all those sets is going to be open. But if you take infinitely many open sets, the intersection of those may or may not be open. And that's where we left things off last time. Any questions or comments about those definitions / results before we move on to some closed set stuff? In that case, before we look at closed sets, we need to know what a limit point is, because that's an important part of the definition. We're going to say that x is a limit point of set A if every epsilon neighborhood of X intersects A at some point, I think I said little b not equal to A. I don't know why I said that. Let's say little a not equal to X. So in other words, if you have a limit point of a set, that means that any epsilon neighborhood of your point is going to intersect your set somewhere other than potentially at the point itself. So let's take a look-see. Let's say A is the open interval from 2 to 5. Question. If we want to ask the question, are the following points limit points? Would you say that the point 2.2, is that going to be a limit point of the set? Meaning, if we take any epsilon neighborhood of 2.2, is that going to intersect the open interval from 2 to 5 at some point other than at 2.2?
Yes.
Alex?
Yeah.
Certainly looks that way. If I take any epsilon neighborhood, I should be able to get some point, I should be able to get some point, in fact infinitely many, in the open interval from 2 to 5 other than at 2.2 itself. So 2.2 would be a limit point. So how about 1.9? What do y'all think? Is any epsilon neighborhood of 1.9 going to intersect our open interval?
Yes.
Yes? Seen some head shakes?
Some do, but not every.
Some do, but not every. Well, is it possible for me to draw an epsilon neighborhood around 1.9 that doesn't contain any points in the open interval from 2 to 5? Yeah, if I take, for instance, v sub, I don't know, 0.01 of 1.9. Go 1.01 to the left and 0.01 to the right of 1.9. That's not going to intersect our open interval at all. In fact, if we take the intersection of those two sets, we get the empty set because there's no points in the open interval from 2 to 5 within this specific epsilon neighborhood of 1.9. So what I would say is that you could say there exists some epsilon such that v sub epsilon of 1.9 intersect our open interval is empty. Whereas if we contrast that with 2.2, we can say for all epsilon greater than 0, v sub epsilon of 2.2 intersected with our open interval is non-empty. And also gives us points other than 2.2 itself. How about 2? Is 2 going to be a limit point of this open interval?
Yes.
Josh says yes. Lewis shakes his head no. Lewis, why not?
Well, I think because no matter how small the epsilon neighborhood you take, you'll still get something on the left of the epsilon neighborhood that's not going to be in there.
But does the whole epsilon neighborhood need to be inside of it? No.
Just has an intersection at some point that's not.
Oh, I guess, yeah, so it always has something on the right, so I guess the same argument says that it is.
Yeah, I would actually say that 2 does work. Mainly because when we say that every epsilon neighborhood intersects A, that means there's at least one point of overlap. If we said is a subset of A, then that would be false, or then 2 would no longer be a limit point of this set. But if I look at the point, and for the sake of argument, I'm going to say 5 instead of 2, just so the graph is less cluttered. It's pretty much the same argument. If I take any epsilon neighborhood of 5, no matter how small, we're always going to get some points that are within this interval from 2 to 5. So I would say that 5, and by the same argument 2, we could say that 5 is a limit point of this set. Yeah, Liz?
Why is it called a limit point?
I don't know. Maybe it has something to do with the limit of something.
No, that'd be too easy. They
That's
just
the
do a
question.
trail.
Maybe a limit point of this. Maybe this definition for a limit point is logically equivalent to saying that there's a sequence of points inside of the set that converges to that point. You ever think of that?
That's because you said it.
Ellen?
Are there any points in the set that are not limit points?
Good question. Are there any points inside of this set that are not limit points of the set? I would say no. I think if you pick any point in this open interval, every single point in that open interval is going to be a limit point. Because you give me a number between 2 and 5, it's always going to be true that no matter what x point you pick, and no matter what epsilon neighborhood of that point you pick, you're always going to get other points within the open interval from 2 to 5 in there. So for this particular set, I would say that every point in A is also a limit point of A.
But there is a set for which not every point in A is a limit point?
Good question. Any other questions? Meaning I'm purposely avoiding answering that because stay tuned for the next page of the packet. Speaking of which, this definition of limit point is going to be useful for us because it's going to give us what it means to be a closed set, where we're going to say that a closed set is a set that contains all of its limit points. So in other words, we can say that F is a set of Adam's grades in this class. If F is a subset of R, we say that F is closed if every limit point of F is a point in F. i.e. F contains all its limit points. So for instance, is the open interval from 2 to 5 going to be a closed set? Meaning, is every limit point of the open interval from 2 to 5 going to be a point in the open interval from 2 to 5? Olivia?
No, because you said that 5 was a limit point, but it's not in the set.
Yeah, we could say that this is not closed. Since for instance 5 is a limit point of the open interval that is not in the open interval. In order to be a closed set, you have to contain all of your limit points. Any point that's a limit point has to be in your set, or you're not a closed set. Question: Does the pair of words "not open" appear anywhere in this definition? No, at least not explicitly. So, something that's definitely a little bit tricky when you start thinking about open and closed sets is we're not going to define a set is closed if it's not open, or a set is open if it's not closed. There's definitely some relationships between the two conditions of closed, meaning containing all your limit points, And open, meaning for every point you're set there exists an epsilon neighborhood contained entirely inside of that set. But it's not as explicit as saying a set is open if it's not closed, or vice versa. So what I would like for you all to do is I want you to look at a couple of examples of sets in small groups and determine whether you think those sets are closed sets or not. Specifically, I want you to look at the following three sets and tell me, do you think these sets are closed or not closed? Let's say closed interval from 2 to 5. I don't know why I'm using the word closed interval. I don't read into that at all. Let's say the union of the closed interval from 1 to 4 and the open interval from 2 to 6. And finally, just for funsies, the integers. Let's go ahead and take a couple minutes and look at these three sets and see if you can determine whether you think each of these three sets is a closed set or not. Meaning for each of these three sets, does each of those sets contain all of its limit points? Or are there limit points of these sets that are missing? So go ahead and take a couple minutes, talk to your neighbors, and see what you can make of these sets.
Okay, the first one's closed. I know that. Because he said it was closed. The second one was open. 2, 6, yeah, 2, 6, and things get done. Or 2,
So
right?
this one,
No, just 2 inside 1 is 4, yeah.
but 6 would not be, and 6 would be, and 6 is not.
That was the Z boy.
It has to be, not me.
Personally, I thought it said the intersection of the two, so it's very like.
Oh, I wrote the intersection of the two letters, but it's not.
It's for every epsilon.
Okay, so the thing with the integers, I think totally.
I mean, you could make it epsilon neighborhood.
Yeah, because you would take an integer,
For the-
epsilon, it's gonna intersect stuff.
Then it might have the
Control
epsilon,
the
No, it does.
so it's whole,
Well, let's say
epsilon neighborhood, and then you use the integers, which is always real numbers.
value, then it'd be like 0.9 to 1.1, and that wouldn't intersect any value.
I didn't
Well,
look at
we
the
wrote that it's
second.
not open, it's not
Exit
closed.
out.
But it doesn't matter,
Oh,
but it doesn't have to that are not closed.
Yeah,
But if you're putting an epsilon
I'm
neighborhood
just
such
like
that it
thinking
isn't
of the
intersecting
logic
value.
for why it's not open, might also be the left why it's not open.
Yeah. Let's think about it.
What else?
So,
Oh, yeah.
every point in the integers, the limit point.
That's what.
Come in second.
Because you can take.
You're not buying
It contains them all. The set doesn't have any limit points, then automatically it does not close. If your set with no limit points, is it true or false that doesn't have any limit points?
We say you have like 2 or 1, 0.5.
I don't like that. That's not
It's actually legitimately a big point.
I'm interested.
I think according to the definition, if it doesn't have video, then it would be closed.
So we can
But
make it.
also, like, Priya said that, I want them to use one.
But it's like,
So
it would, that would
is
be
an
true
integer.
if the definition were worded
And
like,
it's a limit
if
point.
no
But it's
limit
not.
point is outside of that.
Okay.
But the epsilon neighborhood.
Instead of all integers have any
The
limit.
set is not set.
I don't know, you tell me.
No.
There's a limit
I
point
guess not.
outside that.
And that means it's
That
closed.
doesn't mean it's not
because
closed, that just means
That's
that it
it.
contains.
But there are no
It
limit points outside.
might not have any limit points.
They're not integers, they aren't limit points at all. So,
There, I it automatically.
Yeah. Well, they're not so
Set is every.
That would
Yeah,
but not random. You know what? I'm gonna subscribe to the possible error too.
Yes, you gotta be some other.
Alright, because this is a good one.
Yes, you find one.
But it's not close. I don't. Sometimes I read you're gonna have mistakes from like.
Oh, I'm just thinking.
Oh, that.
I don't like, we're just, I felt like the,
Google Journal.
I don't know, you tell me.
the definition of says every limit would have added. Oh, but you're saying that
So,
it's not.
in real numbers, that satisfy that an epsilon neighborhood, that all epsilon neighborhoods in that real number contain integers other than the number of
Oh, yeah.
Is it always the case that any epsilon neighborhood of 2 contains an integer other than 2? Other than 2. Because you gotta intersect at some A
Oh, yeah, 'cause the
I wanna ask that
What?
Yeah.
You gave temporarily and limited. Yeah. Existence is a total matter.
Hey, peace, Brianna, where's it going?
I'm going to raise my hand.
Okay, if we have a set that has no limit points, what does that say about it being?
How did I recognize?
Well, if you don't have any limit points, does that mean you contain all of your limit points?
Yeah, technically.
So you're saying that, so if your answer is no, that means there's some limit points that you're missing.
So yes.
Alrighty, let's come back together. So, first of all, let's look at that closed interval from 2 to 5. Which points are going to be limit points of this set?
All of them.
All of them? All real numbers?
Yep.
Okay then.
Thanks, Adam. You're welcome. Mistakes.
Something tells me that you all don't really believe that. Or I'll have
By
to-
one, you think.
or I'll have to pull this out.
Ooh.
So, what do you mean when you say all of them?
Every point in the closed interval 2 to 5.
Yes. So I could say all x in that set. Yeah, every point in that set is a limit point of the set, and there are no points outside of the closed interval that are limit points. Because give me any point outside of the closed interval from 2 to 5, you're always going to have some epsilon neighborhood that doesn't intersect your set at all. So what do y'all think? Closed or not closed?
What do you think?
Well, he said it was.
I think I should ask you, Adam, what's your opinion on the matter?
I think it's closed.
I would agree. Closed intervals are closed, shockingly enough. How about this one? Closed interval from 1 to 4, union the open interval from 2 to 6, which ends up being this half-open interval. What would all the limit points of that set look like? Laurie?
All real numbers from 1 to 6.
Including 1 and 6? Including both. So Laurie believes that the limit points of this set would be all x in the closed interval from 1 to 6. Which I think I would agree. I think every point in this set is going to be a limit point of this half-open interval. And any point strictly less than 1 or strictly greater than 6, there's going to be some epsilon neighborhood around that point that doesn't intersect our half-open interval at all. So, closed or not closed? Alex gives a very indecisive answer. Amy, what do you think?
I think it's not closed,
Why?
because it doesn't include 6.
Yeah, because 6 is a limit point of the set that is not in the set itself. And I think 6 is the only one that's going to cause that to happen. So since there exists a limit point of the set that's not an element in the set, that means that the set is not closed. So finally, how about the integers? What are the limit points of the integers? Kate?
So I don't think there are any limit points because none of the points in the integers has every epsilon neighborhood intersecting with another integer. Because you could choose an epsilon value between -1 and 1. And
An epsilon value between -1 and 1? I hope epsilon's greater.
Or sorry.
Between 0
Yeah.
and 1.
Yes, sorry. Between 0 and 1, and it will intersect the integers anywhere, so it doesn't actually have any limit points.
Interesting. So okay, if I take, for instance, x equals 1.9, can you give me an epsilon neighborhood at that point that doesn't intersect the integers?
0.01.
That would certainly not intersect the integers at all. Counterpoint. How about 3? Is 3 a limit point of the integers?
No, because you could still choose an epsilon value that doesn't intersect since a can't equal x for a limit point.
Yeah, since we can take an epsilon neighborhood of 3 that doesn't intersect the integers other than at 3 itself, 3 and the 3, and similarly any integer is not going to be a limit point of the integers. So I think I agree with you here, Katie, that I don't think there are any limit points to this set. Josh?
I have a question after we finish the closed question.
All right. Well then, let's ask the closed question. This set has no limit points? Is it closed? David?
Yeah, it is.
Why?
Well, if it doesn't have any limit points, then the criterion can't be fulfilled.
If it doesn't have any limit points, the criterion can't what?
Be fulfilled.
It can't be fulfilled, so it's not closed?
No, sorry. It can be. How do I say this?
It can't fail to be fulfilled?
What's that? No. I just gave a little thumbs up, that's all.
Why are you picking on me? Alex?
So if the set of limit points is the empty set, and the empty set, is there technically then an intersection with this set A, and therefore it would be closed?
Well, you could always say that the empty set intersect with the integers is, almost wrote the integers, that's the union, is the empty set.
Okay. So I don't know if that makes it closed.
It actually does check out. For the reason being, and I'm going to try and restate, Stephen, a little bit what you said.
I was eloquent.
Oh, yeah.
Keep telling yourself that maybe it'll come true.
Yeah, you're very eloquent. You stated the definition of what it means to be not closed is your argument for why it's closed. The reason why I would say that this set is closed is because it is vacuously true that every limit point is contained within the set itself. So in other words, there's no way to say it's not closed because it's impossible to find limit points outside of your set because there's no limit points at all. So it's technically true to say that every limit point, all 0 of them, are contained in the set. Lily, did you have a
I
question?
was just about to say that. I was about to ask if it was vacuously true.
Oh, yeah, I would say it's vacuously true.
So are all unbounded sets like automatically closed?
Good question. Is that a closed set? No, why not?
Because the 2.
Because 2 is the limit point of this, even though it's not in the set. Yeah.
Okay.
So it would be false to say that unbounded sets are automatically going to be not closed. Because you can still have an unbounded set that has limit points. And you could have some, like the integers, that don't have any. By the way, Emily, this answer to your question earlier, yes, you can have sets like this where have points in the set that are not limit points of the set. I purposely didn't want to answer that because I knew we were going to look at this example. Yeah, Josh?
So we have the two examples of our closed sets. The first one contains all of them, and the second one contains no limit points.
And thus contains all of them because there are no limit points that we need to consider.
Right. Is there something in the middle where like there are some limit points, but it's not the whole set?
That would be a set that has anything in this open interval is going to be a limit point of this set. But any integer other than 1 and 2 is not going to be a limit point of this set.
Gadzooks.
Quite. Happy?
I'm a little bit confused by the way we're defining closed with like the integer example, because we said it's like vacuously true that every limit point is inside of that. But isn't it just as vacuously true by the same logic to say that every limit point is outside of the integers?
Yes.
And wouldn't that violate the definition?
No.
If every limit point of the set existed outside of the set?
If you don't have any limit points, that doesn't violate the definition. Because if there's no limit points, then it would be true that every limit point is both in and not in the set. And since every limit point is in the set, it is closed. Break your mind around that one. So Peter, let me rephrase a little bit. If you assume that your set has at least one limit point, then the fact that every limit point being outside your set would automatically violate being closed. But if there are no limit points to speak of at all, then it's impossible to show that the set is not closed, because the set being not closed means there's some limit point outside of your set, which isn't true for the integers because there's no limit points either inside or outside. Therefore, it's impossible for it to not be closed, and therefore technically it is closed.
Okay.
So, what does this mean that the integer is a closed set? Because
It means
On
it
the other-
contains all its limit points.
well, but in the other examples, it kind of denoted this closure, right? That it starts here and stops here, and that's all there is to it. But the integers is an infinite kind of thing. So there's not really that same sense. So what exactly is that telling us?
Intuitively,
Yeah.
it's impossible for a sequence of integers to converge to an integer unless that sequence is eventually constant. That's another way to kind of rephrase. Y'all asking questions. So in the next pack, we're not going to do it in this packet, but in the next packet. So after break, we're going to be looking at. What are you going to be looking at? Oh, good, I'm recording. We're going to be looking at the relationship between sequence convergence and our definition of closed. And it's going to turn out that an equivalent definition to a sequence being closed is that it has a set being closed is that every sequence of points in the set that converges to something has to converge to a point inside of that set. And so another way to phrase it would be to say that if you have a sequence of integers that converges to something, it has to converge to an integer. You can't have a sequence of integers that converges to, surprise, pi, for instance.
-112.
Or to -112, for that matter. Question. And go ahead and take a minute and talk with your neighbors about this one. Can a set A be neither open nor closed? And similarly, can A be both open and closed? take a minute or so, talk to your neighbor, and see, is it possible to have a set that fails both our definition of open and our definition of closed? As well as, is it possible to have a set of real numbers that satisfies it is both open and closed at the same time? If you turn the page, I give you a place to think about that.
Half open interval.
Yes,
They're
because
9.
this is not closed because it's two and it's not open because it's that works.
Okay.
Wait, I have no idea.
So you claim that any real number you can find in an epsilon neighborhood. Everybody's looking at me and I'm going to bend over here. So you claim if I take any number in that set, then any epsilon neighborhood of points in that set have to be contained within that set?
Yes, yeah.
And do you claim that this set contains all of its limit points?
Set
Well
up
then.
real numbers.
Sounds good to me.
Great. Close because every limit
It's a really good movie.
is contained within the set. Every real number.
Every movie
And
might
it's open because
That being said, answer the question.
okay.
We'll talk about half open intervals.
The null set.
Unless you had a question.
Wait,
I'm sorry about that.
With the closure roll, 1 to 6, but no, well, half close, half. They picked 6 1 to 6. Maybe we'll just open it at the point that you find.
When you go into
You
ES,
find your roll.
go down up the front.
Oh, yeah, trivially, but.
And then we're gonna say
Well,
this
one,
tomorrow.
that we like.
Oh, wow.
Yeah.
That's a long drive.
But we just.
She was, but she
That's
had
fine.
left. Oh,
That's
she
fine.
was really fast to go. Yeah, she mentioned St. Louis.
Yeah, sorry, I should say, in order to say that your set is open, it has to be able to find a epsilon neighborhood for epsilon strictly greater than 0, that's, subset.
St. Louis, Missouri.
It's about a 7-hour drive.
Technically,
That makes
if
sense.
epsilon is E0, then every single set would be open, because you take any point in any set, it's epsilon neighborhood, which is that makes it out of
And I think
Yeah.
it's 10 hours to the span.
Both open
Stop.
intervals.
Okay, yeah, fair.
Oh, so they kind of, we divided over the buses.
Can you imagine
So
that?
anyway, I'm saying.
It contains a lot.
The whole thing like
Yeah.
There is
We went to
Yeah,
Mackinac
definitely.
Island once for band down for the.
What did you bring?
Yeah, if I could do all
I only did it for like 2 years in middle school. and then I-
Alrighty, let's come back together.
like 2 semesters.
Is it possible, was anybody able to find a set that is neither open nor closed? Sorry, Josh, I just want to spread around a little bit. Peaches.
The second example that we just,
This one?
yeah,
We know it's not closed. Why is that set not open?
because the point 1 is in the set and doesn't contain, and the epsilon neighborhood isn't contained in the set.
Yeah, if we look at this half open interval right here, we know it's not closed because it doesn't contain a limit point of 6. We also know it's not open because 1 is in the set, but no epsilon neighborhood of 1 is a subset of the half open interval. And so that's going to tell us that this set is not open as well as not closed.
So we can generalize that to say that any half open interval effectively is that language by that notation.
I'm going to say yes, even though the answer is technically no, but yes. I'll explain why in a second here. Is anybody able to find an example of a set that is both open and closed? Brianna?
We said R.
GG now. So first of all, you claim that R is closed because it contains all its limit points. You also claim that if I give you any real number, you can find an epsilon neighborhood around that point that that is contained within the real numbers. Sounds good to me. What?
The empty set also works.
Oh. So you claim that the empty set contains all of its limit points,
Yes.
because there aren't any. You claim that if I give you any element of the empty set, you can find an epsilon neighborhood around that point contained entirely inside the empty set.
Yep.
Vacuously. Empty set would also work. It is both open and closed, and hence we are going to give these sets the name. Which may seem silly, but that is an actual term that mathematicians use. I can assure you it is.
Wow. This is one of the reasons mathematicians are accepted in general.
So, moral of the story. Just because a set is open does not automatically make it not closed, and vice versa. You can have sets that are neither. You can have sets that are both. Any questions or comments about that?
Are there any other words to describe sets that are both open and closed?
Yeah, opposed. No. No. No, it's usually, clopen's usually what is used. Or just, or if you think that it's silly, open and closed. All right, so Dr. Gerstle, you've been teasing us enough. You said that there is a relationship between open and, to answer your earlier question of is every half open interval have to be neither open nor closed? That is both open and closed.
Oh, because it's just empty set.
Because it is the empty set. But any non-empty half open interval will be neither open nor closed.
That just seems silly.
It is. But it is technically an example, and that's why I said technically it's possible, but practically speaking, half open intervals are always going to be neither open nor
So
closed.
it's a yes with an asterisk, and an asterisk denotes no.
Yes.
Peaches?
What if we looked at the set containing just the non-negative real numbers? So it'd be like closed 0 to...
Non-negative, so like that?
Yeah.
Good question. Is that set closed? Does it contain all of its limit points?
Yes.
Is it open? And that answers your question. It is not open because 0 is a point in this set, but there's no epsilon neighborhood of 0 contained entirely inside this set. Mainly because any epsilon neighborhood of 0 is going to contain some negative numbers. Are there questions or comments?
In that example, where you define the empty set, didn't we just say that the empty set is clopen?
Correct. But your question was, do all half-open intervals have to be neither open nor closed? And my answer is, well, technically this is a half-open interval that is the empty set, which makes it both open and closed, as opposed to neither open nor closed.
Okay.
So Dr. Gerstle, what is this relationship between open and closed? Because I'm unsatisfied with this. Well, turns out that there's a nice theorem that relates the two conditions. And if we flip to the back page, if you recall, we said that the complement of a set is just the set of all real numbers that are not in your set. So basically everything outside of your set. And it's going to turn out to be the case that if you take the complement of an open set, you're always going to get a closed set. And if you take the complement of a closed set, you're always going to get an open set. Which leads us to this. could say that a set U is open if and only if the complement of U is closed. And similarly, U is closed if and only if the complement of U is open. And
Does this apply to Clopen?
sure. If you have, basically, we could say that a set is clopen if and only if its complement is also clopen. Because if your set's clopen, then it's open, which means the complement's closed. And if your set is closed, then that means the complement's open. So if your set is both open and closed, then the complement has to also be both open and closed. So for instance, what would the complement of the real numbers be?
The empty set.
What would the complement of the empty set be?
The real numbers.
Every real number that's not a real number, well, that doesn't make sense, so that's the empty set. All real numbers that are not elements of the empty set, well, no real number is an element of the empty set, so the all real numbers that are not elements of the empty set is just all real numbers. That would tell you, this gives an example of the complement of something clopen has to automatically be clopen as well. That's a stretch. That's a stretch, Lily. Makes it wild. So we said that this set would be open, right? So according to our theorem, the complement should be closed. What is the complement of the open interval from 1 to 5?
The union of the set negative infinity to 1, including 1, and from 5, including 5, to positive infinity.
So in other words, the complement of this open interval ends up being the union of these two closed intervals. And it may shock you to learn that the union of two closed sets has to be closed. So this set being the union of these two smaller intervals is going to contain all of its limit points. And similarly, we start with something close. If we take the complement is always open. Have a good spring break, everybody. We will prove this theorem Monday after the break. And once we prove this theorem, we're going to move on to talking about what's the relationship between closed sets and sequences. And that's going to lead us to talking about what does it mean for a set of real numbers to be compact.
Does anybody know?
Have a good one.
Yes. Please take